Hi, I'd like to introduce to you PCTRAN NuScale. PCTRAN is a nuclear power plant simulator, and NuScale is a small modular reactor developed by the NuScale Corporation. It was the first and only one approved, selected by the U.S. Department of Energy, and now being reviewed by U.S. Nuclear Regulatory Commission for design certification. It is basically a PWR. Here is the core, and the white vertical assembly are the control assemblies, and the red field symbolize located the lower part of the reactor vessel. It is basically a pressurized water reactor, but the difference is the pressurizer is located inside the reactor vessel at the top, and the two helical core steam generators also located inside the reactor vessel. The feedwater line going into the primary side, and this helical coil spiral around the reactor downcomer, becomes steam into the turbine and the generator. The condenser water is pumped back into the reactor. The primary containment is different from the conventional PWR. It is not in the atmosphere, but a vacuum pressure, so it's insulated. And outside the containment, there's a large reactor building pool. The entire module is underground, up to 12 modules for one power plant. The thermal power is about 160 megawatt thermal, and converted into electricity is about 45 megawatt electric. Part of the steam can be used for desalination, and the gain operation ratio is about 9.5 times. That means 1 kilogram per second will produce 9 times of distilled water. And now let's run it. We can click at the runner sign here, and on the lower right side you see the atom. Electrons are rotating, and there's 1 that means real time. Simulation speed is the same as the reaction speed, chain reaction speed. And for education, we can accelerate it to 2, 4, 8, up to 16 times faster. And that's so that we can demonstrate transient in a classroom at a faster speed. Just like any other PWR, we can control the power by inserting rods. And in this PCTRAN design, most of the rods are outside the core. So start with 98%. Suppose we set it to 97% at the speed of 1% per minute. You'll see the rods go in slowly. All right, and the power will go down, originally 100% to 99%. And there's a very sophisticated control system and a pressurizer, and there are heaters and a spray. If the pressure is too high, the spray will turn on. If the pressure is low, the heater will turn on. And the other control of the steam generator feed water and steam pressure to keep the chain reaction balanced. In actual control of a PWR, we do not do it from the primary side. Instead, we control the turbine generator. Suppose we reduce it to 80% and close the window, continue to run. And now I'm doing too fast, 16 times fast. So let's do it. The moderate faster speed, 4 times faster. You see the power go down. In the meantime, the pressure and the level of the reactor is controlled by the chemical and volume control system. We can see the transient variables by choosing the transient plots. First, let's see the power. The variables are in alphabetical order. Let me choose core power, neutron flux, and the turbine power. They are all in percent nominal. And let me choose the time scale to be 1,000 seconds and click OK. You see, first I did the power control by inserting the rods, and later I control it by the turbine side. So suppose we change the power again to 80%. We'll see the power of the turbine drop to 80%, and then the reactor, the neutron flux and thermal power follow the turbine demand. So we can control the NuScale reactor just like any other PWR. And being a small modular reactor, it's unique that we do not rely on the offsite power, AC power. So for a case like Fukushima, total loss of AC power, then the design is there's a large pool of reactor building water. Let's shut down the reactor, click the button, the reactor shut down. And suppose we lose offsite power, so we will lose normal feed water and the main steam isolation valve are closed. Then the operator can initiate, that could be done automatically, the passive or decay heat removal system. So steam in the steam generator will go into the pool, and their heat exchanger, they're physically located inside the reactor building pool, will be condensed and returned to the feed water, so that the decay heat right after reactor shutdown is about 3% or about 4.7 megawatt. It will be removed by the heat exchanger. If both trains are operated, they're redundant. One is enough, but two will be available. So the core decay heat will be removed by the passive heat exchanger. You see the pool water originally is about 20 degrees Celsius, and now it's slowly increasing, heated up. So operator do not need to do any emergency procedure or under any pressure. The reactor is simply cooled. And of course, this will slowly heat up till boiling, 100 degrees. Takes about a day or so. We already run it 4 times faster than the real time. But we have previously stored the condition. So the case initial condition 8 is 1 day after reactor shutdown. You see, the water is basically still in the reactor, still filled to the top, but temperature is start boiling 100 degrees. And I can show you another condition that I previously saved 3 days after shutdown. And we can accelerate the cool down by opening the reactor vent valves. All right, so the steam will fill up the containment. Remember, containment was originally vacuum, and now it's filled by reactor coolant. And the hot water in the containment transmit by the conduction to heat the pool water. In the same time, steam is cooled by natural circulation through the heat removal system. So the water is boiled to about halfway here, and the operator can simply, sit there and make sure everything is going okay. And let me show you. Sometimes 3 days or 30 days. Okay, it just now was 3 days, and how about 30 days, a month later? Click OK, and you see most of the water already boiled to the bottom of the vessel. But it's okay, because now the air inside the containment is hot, and by natural convection and the conduction into the reactor building, the reactor still under control, and the core is filled up with still plenty of water inside the vessel. Well, those are the loss of offsite power condition, and we can show you that suppose an accident in reactor safety, we define accident against the transient is something major, a pipe break or something dramatic happen. And let me show you one accident we call malfunction. There are 20 categories of malfunctions. Anything possible are included: a tube rupture, steam generator, or pipe break, a steam line, or feedwater line. And let's try the steam break. I choose number 3, that steam line break inside the containment. Set, and you set the break size 100 centimeters square. Click OK and close it. Now we have a pipe break. we're losing 30 kilograms per second of steam inside the containment. It's a reactor shutdown because of low pressure. Oh, by the way, the original pressure of the reactor is 12.5 megapascal. That's about 1800 psi in British unit. And here the reactor protection system shows that we have a low pressure trip. So react coolant, let me speed it up to 4 times. Okay. Suppose we lose offsite power again. The steam and the feed water are isolated. And we lose the charging, and let down is isolated. So we're losing the react coolant through the steam line into the containment. At this time, the operator may decide to initiate the passive decay heat removal system. And believe it or not, bigger break is more controllable or safer than a small break, because the vent valve, if we open them, reactor vessel vent valve, it will speed up the coolant loss, but also make the heat removal faster. Okay. So the coolant loss is through the brake and vent valve. And let me speed it up so we do not spend too much time in this demonstration. So the coolant will fill the containment water level. Let's put it maximum. And the pressurizer now become empty, and the water level fall inside the vessel. The containment water level now go up. And reactor core water level go down, right? Because your coolant loss. Pretty soon, we'll actually see that containment water, there are 2 recirculation valves between the containment and the reactor vessel. The recirculation valves design preserve the water inside the containment. So when this level is higher than the vessel, we open these 2 valves, so the water will go back into the core. You see, physically, the water level is above the top of the fuel. So forever, there's water keep the core submerged. In other words, the fuel will never heat up. See, here's the fuel temperature, and here's the water temperature. So this NuScale natural circulation small modular reactor is safe forever under whatever condition. And the small modular design with 12 units in one building site. The module is prefabricated and can be shipped by a freight train or a large barge. So that will be the new generation of power supply to remote area as well as heavily populated metropolitan, because it's safe and it's modular design. It would be a new way of providing non-carbon releasing heat energy source. See, now the water level is approaching, let's see, this is 6.5 meter, and here is the core water level is 8 meters. Sorry, I cannot speed up any faster for now, but pretty soon you'll see that now it's a point that we can not yet. See, this is 7 meter, this is 7.8 meter. But as soon as you know, the animation is not exactly valid. Okay. Pretty soon, it's 7.8, 7.5, 7.6. Bingo. See, the water is going back into the vessel. Alright, so that's all I want to show you. You can try that yourself, but download from the web cannot run over 300 seconds. So hope you get an idea of NuScale. Thank you.